Okay, good morning. We had a very good office hour yesterday, so if you're having trouble along the way, join those office hours. It was very productive, I think. Okay, we're going to start with where we left off yesterday. Multiple point charges. We're looking at a force on a charge from multiple point charges and thinking a little bit about where the direction comes into play with these vector quantities. So let's take this example. We've got 3 point charges on an XY coordinate grid. And we want to know what's the net force on Q2. So maybe I should give you a minute to think about this problem. So there's the setup. Q1, Q2, Q3 at the 3 corners of a square. Q1 and Q3 are the same charge, magnitude, and sign, and Q2 is a little bit different. So go ahead and think about that for a minute. See if you can find the net force on Q2. So you're thinking about the directions of the forces. So charge 1 and 2 are going to interact with each other, and there's going to be a force on Q2 due to Q1. They are going to repel each other. So there's going to be a force in this direction. F between charges 2 and 1. And then there's going to be a force between 2 and 3. They're going to repel each other in this direction, right? So you need to find the magnitudes of those forces first, and then do some vector addition and figure out the net force on Q2. So as I plug in the numbers here, K is our constant 8.99 times 10 to the 9th. Our charge is 2 microcoulombs, that's 10 to the minus 6, and 5 microcoulombs, that's 10 to the minus 6 coulombs on each of those. And our distance is 0.1 meters, and we square that. So I get 8.99. Now I know the direction is straight up. So since I've defined my positive X and positive Y directions here, I'm just going to say that the force is 8.99 newtons in the Y direction, or straight up. This is just the force between charge 1 and 2. Just the force between charge 1 and 2. Okay, so now we do the same thing for F2, 3. First, you find the magnitude. And it turns out to be the same, right? And then we assign a direction to it. And we know from the situation, it's to the left, or negative I prefer 8.99, but it won't matter too much. Newtons, and this is going to be in the minus X output here, minus X hat. Or if you want to write to the left, that's fine. But don't tell me it's negative to the left. I don't know what that means. It's negative X hat, or it's to the left. Tell me in words, or define it a positive direction and put a sign in there. Don't do both. Okay, so we know that one is to the left, that one is up. Now we can put them into components. They're already in components, right? They're already in IJK, XYZ components, whatever, however you want to call it. But so we can combine them now. So our net force is just the sum of the two, right? And it's going to be okay. If you want to find the magnitude, then it's the square root of 2 times that, right? Because they're both the same magnitude. It's a square. So I think that maybe that helps a little bit. But you know, the way I like to use this equation is just to find the magnitude of the force, and then look at the situation, look at your diagram, and figure out, are those forces repelling, right? Are those charges repelling? Then the force must be this direction on this charge, right? Are they attracting? Then the force must be this direction. And then you assign the direction from looking at the picture and the situation involved. Okay. All right, if you want a little problem to do after class, you can try to think about what charge would you put at the empty corner of the square to make the net force on Q2 0. I'm not going to do it, but that's a good follow-up to this. It depends. The question is, can you just find the magnitude of the force? It depends. If I'm asking for a force, anytime I'm asking for a vector quantity, your answer to be complete should have magnitude and direction, unless I'm specifically asking for the magnitude of the force, but should have magnitude and direction. You can give the magnitude and an angle, draw a little picture, give me the magnitude and the angle, that's fine, or give it to me in component form. I'm not sure what you mean by using vector operation to calculate the force. These are vector quantities. So the force F21 here, that's a vector, and F23, that's a vector. And in order to combine them, you have to use your vector addition rules, right? Break them into components, add them up, something like that. Okay. Let's do this one. We've got two identical conductive spheres, L and M. One of them is charged up to 4 coulombs. The other one has no charge on it. We're going to bring them together, let them touch each other, then separate them. And we want to know what's the charge on M after we do that. Okay, so we've got this situation. We're going to bring them together so that they touch. Then we're going to separate them again. And we want to know what's the charge on each one after we do that. Oh, sorry, I didn't launch the poll yet. Poll. There you go.
Professor, could you scroll down your screen a little bit so we can see the options?
You can move the poll, I think. Just drag, is the poll in the way?
Oh no, that's good now. Right.
I will tell you that this is only true because the two spheres are the same size. It says two identical metal balls, L and M. So because they're the same size, this is going to be true. We'll learn in a week or so, we'll learn that when they're different sizes, the charges split differently, and we'll be able to figure out what the charges would be on each of the spheres at that late in a couple of weeks. We'll know how to do that if they're different sizes. Okay, let's close.
What was the answer?
Let's close this out here. The answer is, let's see. The answer is 2. They'll both be 2 coulombs. Okay, so let's look at that. We've got, this one has 4 excess charges on it, right? They want to get as far away from each other as they can. So they go all the way out as far as they can on the surface of that sphere, as far apart as they can. Then when we bring them together, it's like one big conductor now. So those 4 positive charges are repelling each other. These are conductors. They're free to move around. And I know that positive charges aren't moving, but you can think of it that way if you want. It doesn't matter. For these purposes, you could think of positive charges as moving, negatives as moving. It doesn't matter. You get the same result either way. So now those positive charges want to get as far away from each other as they can, and we've increased the size of our conductor by touching these two spheres together. So the charges are going to split. They're going to be a couple over here, and they're going to be a couple over here, as far apart as they can get from one another, because they repel each other and they're free to move. Now we separate them, and so this one has two of the charges, and this one has two of the charges. Okay. Question about calculating net force. Yeah, we cannot calculate that now. So the question is about calculating a net force between a charged object and a neutral object due to the induced charge separation. And we really can't do that. I guess we could if we knew it was a conductor and we knew the diameter, and we could assume that, make some assumptions about all the charge being at one edge or the other edge of that sphere, and we knew the diameter, then we could probably kind of come up with a close estimate of the force. But for our purposes, when we calculate forces, they're both charged objects, and we use Coulomb's law. Okay, I think I answered that. If M is an insulator, well, what happens is the charges can't really move into M except where they're actually touching. So maybe M would pick up a couple of electrons or lose a couple of electrons, I guess I should say in this case. And so right at the point where M and N touch, because if M was an insulator, right at the point where they touch, the positives would want to pull an electron or two over. And so M might lose a couple of electrons. But if we're talking a lot of charge here, we're talking 4 coulombs of charge is a huge amount of charge. And so the few electrons that we're able to transfer over when they make contact wouldn't affect that at all. Now, if it was a small amount of charge and a few electrons transferred, maybe it would have some impact, but very few. It would have to be at the point where the two objects are touching, and then maybe a couple of electrons right at that point where they're touching would get pulled over. And once that happened, then you'd have a slight positive charge. You wouldn't get more electrons going over. Okay, good. All right, next one. Let's got another one. So now we have 3 of them. Let's see, +4, -2, and 0. An insulator can accept a charge, it can lose a charge, but once the charges cannot move throughout over the surface area or throughout the volume. Once they're where they are, they stay there, unless you're rubbing it against something and it can be removed that way from rubbing with something else, right? The other material can either grab an electron or lose an electron to it. Okay, so here what are we doing? We're bringing the 4 L and M together first, then separating them. Then we're bringing M and N together and separating them. And we need a pole, don't we? I've got to stay on top of these poles. Okay, I've got over 70% voted. I'm going to end that. And so most people said half a coulomb, and that is correct. So let's take a look at what happens here. We bring L and M together. You have a +4 and a -2. So there's a net charge there between all of those charges of +2. So they're going to split up. So you get +1, +1, right? And so you have a +1 and a 0, and they are going to split up. So you get a half and a half. Okay. Now, maybe this is a good point to talk about quantized charge. So when you are charging something, you move an electron over or remove an electron, right? You add or subtract an electron. So the electron is a fundamental particle in physics, right? Physicists are always trying to figure out what's the world made of and what holds it together. And how do you figure out what's the world made of? You start picking things apart, right? At one point, they had it down to atoms. They said, oh, if I had a block of gold and I keep breaking that block of gold into smaller and smaller pieces, eventually I just have a grain, a little tiny piece, and I keep breaking that up. Eventually I have one atom of gold. That still has the properties of gold, right? The same melting point, the same conductivity, right? That atom of gold is still gold. But then people figured out they can break up atoms. And what's inside of an atom? There's a proton, a neutron, and an electron. And then they figured out that they can break up protons and neutrons into quarks. Well, we can't break up quarks, at least not today. Maybe in the future we can. So quarks, we say, are fundamental particles. They are the building blocks of all matter. And we can't break up an electron. An electron, we say, is a fundamental building block of matter, right? If we could break up an electron into smaller things, then we would figure out what's in there, but we can't at this time. So we say that it's a fundamental particle. So when we charge something by adding or subtracting an electron, we have to add or subtract the amount of charge on an electron. We cannot have half an electron of charge on something because we can't have half an electron, right? We can't break it up. So we say it's a quantized value. Electric charge is it can be here, 0 electrons, right? We can add 1 electron and the charge jumps up to here. It can't be in between. It can have 1 electron or 2 electrons of charge. It can't have 2.5, right? It's like standing on a ladder. You can stand on the first step or the second step. You can't stand in between, right? And so that's true with electric charge. But this is a coulomb. This is not 4 electrons on this on L. It's 4 coulombs of charge. A coulomb is a huge amount of charge, lots and lots and lots of electrons. So we can have half of a coulomb or much smaller divisions of a coulomb. Okay, let's do the next one. One more just to see if you got it, and then we'll move on. So we bring, this time we bring L and N, same three spheres, same three charges, but this time L and N come together first. And then we separate them. I'm going to bring it, I'm going to put this one back. We already did that problem, right? Oh, you need the poll, don't you? Got to stay on top of this. Question, if you only had one extra electron between the two metal balls instead of a whole coulomb of charge, what would it do? Well, it would have to pick, right? It would probably be moving around across, when you brought those two metal spheres together, now that's one big conductor. So that electron is just going to move around, it depends on the temperature. If it's hot, it's going to be moving fast. If it's cold, it's going to be moving a little slower. It's just going to be moving around. And then when you happen to separate them, maybe it's going to be on this one, maybe it's going to be on this one. It's going to be one or the other. Okay, I think we're good here. It looks like most of you are there. So it's going to be neutral, right? We've got two spheres. One has -2 charge, one has +2 charge. Okay, everyone got to this point. Okay, I think, because we've already done the first one earlier. And so this is going to be 0 and 0. Right, so I guess I should go back and, what was the first one? 2. There we go. Okay. All right, so we're seeing, this is a situation where we're seeing force applied at a distance, right? In physics 4a, every force we dealt with in physics 4a, except for one, the objects had to be touching, right? The normal force was an interaction when two surfaces touched each other, right? Friction was an interaction when two surfaces touched each other. All of those forces we dealt with were from touching, things touching each other, except for one. We had one force that could reach in from a distance and act on another object, and that was the force of gravity. And so now we're seeing our second force that can reach in from a distance and exert a force on something, and that's the electric force. And so it's hard to wrap your mind around that, right? It's how can two objects at a distance, magically exert a force on each other? So we have a model that we use, right? If we remember back to 4a, if you remember back to four-way, we have a model. And our model is that it tries to help us picture how this could happen. How can two objects interact when they're not touching each other? And that's fields. So we say some massive object fills the space around it with a gravitational field. So we draw these field lines. And then we say any other object with mass interacts with that field, and it feels a force because of that interaction. And we know that gravitational forces are attractive. These would be our gravitational field lines, right? And what direction do our gravitational field lines point? They point the direction an object with mass would go if we stuck it at that location. So if we stuck a mass over here, it would go towards the other mass, so our gravitational field line points in that direction. The direction a massive object would go if we put it there. Okay, so that helps us kind of wrap our heads around the fact that how can these two objects exert a force on each other without touching each other? One of them fills the space around it with a gravitational field. The other one interacts with that field and feels a force because of that interaction. And so our force here was G m1 m2 over r squared. And our electric force, we're going to do the same thing. We say an object with charge fills the space around it with an electric field. And any other object with charge in the presence of that electric field interacts with that field, and it feels a force because of that interaction. Okay, what direction do our field lines point? They point in the direction a positive charge would go if we put it there. Somebody had to pick, right? So that's our definition. So if we put a positive charge right here, what direction would it go? It would go away from this. So our field lines point radially outward from a positive charge. And what if I had a negative charge there, creating an electric field? Negative charge filling the space around it with an electric field, those field lines would point radially inward because they point in the direction a positive charge would go. If we put a positive charge here, it would go toward that negative charge, right? Okay, so there's our force of gravity, and our electric force is K Q1 Q2 over r squared. Now, what did we do with gravity? We said, you know, sometimes we get tired of doing this calculation all the time. We are on the surface of the Earth, and every time I want to know how much something weighs, I'd have to do this calculation, right? Put in G, the mass of my object, the mass of the Earth, the radius of the Earth squared, right? So on the surface of the Earth, we get tired of doing that same calculation over and over and over. Every time we change the mass of M1, right? I want to know how much does my coffee mug weigh. I use the mass of my coffee mug in this equation. I get the force of gravity, I get the weight of this object. I want to know how much my phone weighs, I do the same thing, right? Everything is the same except for this one mass right there. So what I do instead is I say, let's define what the gravitational field is at the surface of the Earth. The gravitational field is g m Earth over r Earth squared. And then the force of gravity is just m times my gravitational field. And now I can do the same thing with forces. Okay, so let's say I had some complicated charge distribution. And I want to know, I'm going to put a force, I'm going to put a charge over here. I'm going to put a charge here. And I want to know what the force is on that charge. Well, I could go through and calculate the force from Q1, the force from Q2, the force from Q3, the force from Q4, and I could do the vector addition and add them all up. But then I say, oh, wait a minute, now I'm going to put a different charge here. So I had, I put a 2 microcoulomb charge. Now I want to put a 3 microcoulomb charge there. I'd have to do the calculation all over again. Now, oh, wait a minute, no, now I want to put a 6 microcoulomb charge there. Right, I could keep, every time I change that charge, as long as all those other ones are staying the same, I can just find the electric field at this point. And then I can say my force is equal to the charge that I'm sticking at that location times the electric field that exists at that location. So that's what I do. And so that means that what is my electric field? My electric field must be K, Q, if this is Q1, this would be Q2. This is the electric field from a point charge. Okay. This is this is just an example. Okay, this one over here, that's just an example. If I was going to find the electric field in this case, right, what would I do? I would use this equation with a Q1 here, and that would give me the electric field from 1, right? Then I would use this equation with a Q2 here, and that would give me the electric field from Q2. Then I would use it with the 3 here and get the electric, maybe 3 is negative, get the electric field from 3 here. Then I would use this with the 4, right, and get the electric field from 4. So if 1, 2, and 4 are positive, the electric fields would point in the direction I drew them. If 3 was negative, it would point this way. Then I do my vector addition and add all of those up and get a net field. You see what I'm doing? This equation over here is for one point charge. So I took this equation and I said, my field, Q2 is the one that's fixed, okay? That's creating an electric field at the location of Q1. That's why I have a 1 and a 2 here. Yes, field is similar to force. We can just add them up. How do we add them? vectorially, right? There's a vector quantity. In fact, let's take a look here. Where are my vectors in this equation? F equals QE, right? Where are my vectors? F is a vector, and E is a vector, and Q is a scalar. So F points in the same direction as E if Q is positive. So here you have to put the sign in, right? This could be positive or negative. So if Q1 is positive, if I'm sticking a positive charge at some location in space, right? At some location in space, I know my electric field points up. At this location where my finger is, I know the electric field points up. So if I put a charge there, Q1, the force on Q1 is going to be up if Q1 is positive, right? So that F and Q will have the same sign, right? If Q1 is negative, it's going to flip by 180 degrees. The force is going to be 180 degrees opposite the electric field. Okay? All right, let's do this one. So we have some rules for field lines. R is the distance from Q2 to your point of interest, right? The place where you want to know what your electric field is. R is the distance from Q2 to your point of interest, where you're going to put Q1. Okay? All right, let's take a look at this. So we're going to learn some rules now for how we don't just draw electric field lines willy-nilly, right? We've got some rules for how we draw them, and that way the drawings are kind of helpful when we look at them. When we see drawings of field lines, they tell us something, right? They have some information in there. So this diagram is drawn. They've got some charges here. There's two positive charges and a negative charge in between them. And we've drawn the field lines, right? And so what we want to do is come up with, at the different places here, A, B, C, where are they, up to H, we want to know what's the direction of the electric field at those locations. Does anybody spot any problems with this worksheet?
West is in the wrong direction.
Yes, they got their east and west. East and west are backwards here, but that's okay. Okay, so if we're standing at point A is right here. If we're standing at point A and we have our electric field compass out, what direction does the needle point? It points south. That's correct. No, we're not going to use a pole, but thank you for reminding me. There are too many here to do a pole. Okay, so if we're standing at B and we have our electric field compass, it's going to point south, right? C and D, north. E and F, where are E and F? E is up here. North. F. And G and H. I'll give you a minute to get caught up if you're still thinking this through. So when we draw our field lines, they're these sweeping curved lines, right? But what they indicate is if we were standing at that location, the electric field points tangent to the field line. The electric field points tangent to the field line. So if we look at this, sort of summarizes electric fields. Electric field lines originate on what kind of charges and terminate on what kind of charges? Right, we talked up here about the fact that the electric field points the direction a positive charge would go. So because positive charges repel each other, the electric field lines have to originate on a positive charge, right? And move away from them, and they terminate on negative charges like I've drawn here. So they, this would be positive charges. And this would be negative. And it says sometimes these charges are far away and do not appear in the drawings, like here. So we've got these lines are going off somewhere, right? Maybe they're going, maybe this line is going way off and coming back in over here, right? No, those are going the same direction. That's not happening. Oh, it's coming in over here, right? Maybe this was looping way out and then coming back there, something like that. So oftentimes we have in our drawings, lines that don't originate or terminate because far away there's a charge somewhere that those lines are coming from or terminating on. Okay. The direction of the electric field at a point is, this could be sort of have two ways of answering this. I think what they're looking for here is tangent but another way of saying it is that it points in the direction a positive charge would go. Yeah, even at infinitely far places, electric field lines always originate and terminate on charges. That's how we get electric field lines. We don't generate them with other things at this point here. Okay, and what do we have here? The magnitude of the electric field is greater in regions where the field lines are. Where do you think the electric field is the greatest here? Out here or in here? In here, right? So that's where the field lines are close together. Where the field lines are close together, it indicates a strong electric field. So the density of the field lines, the magnitude of electric is greater in regions where the field lines are more dense, right? Closer together. And then it says here, another property not apparent from the drawing is that the number of lines that originate or terminate on a charge is proportional to the magnitude of the charge. So if you've drawn your diagram correctly, and this is drawn correctly, how many field lines do we have coming from this? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 lines coming from this one. And how many lines do we have coming from this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 lines coming from this one. So these two charges would be the same. The magnitudes. Now this one in the middle, what does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops, what happened? Lost my OneNote. It'll be back. Hold on. Share. Sometimes it decides to close on me. There we go. Okay, so this one in the middle is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 12 on the other side is 24 lines. So it is twice as much. The magnitude of that negative is twice. So Q negative is equal to 2 times Q positive, because I can tell that just by counting the field lines. Okay, so we'll take a 10-minute break, and then we'll pick up again and at about 11:03 or so. I'll pause the recording here. Okay, we're back. We're talking about electric fields. Oh, let's do this. Applications. So one of the applications of electrostatics is photocopy machines. Maybe you haven't given a lot of thought to how a photocopy machine works, but the key is that there's a material that they call it a photoconductor, this yellow band here there on the image, a photoconductor. And so when it's exposed to light, it becomes conductive at that area where it's exposed to light. That's kind of the key to making this whole thing happen. So if you sprinkle negative charges over the top of it, and you have the bottom plate is grounded, then positive charges appear there, or negatives move away to ground, however you want to view it. And then you shine light on a piece of paper, and the black ink absorbs the light, and the white part of the paper reflects it. And so every place that was white gets exposed to light here, and that electric charge goes away. Then you sprinkle charged particles that have your ink, that contain ink, that's your toner, right? You sprinkle that on top, and they are attracted to the negative charges on the drum. And then you run your paper through. Your paper would be is given a slight negative charge. It picks up the toner, and then it goes through a heater or something that sets the toner and causes it to become permanent on the paper. So it deals with a couple of things. The key is this material that becomes an electrical conductor when it's exposed to light. That's kind of the key. And you shine the light off the paper. So areas that have black ink on them absorb the light, they don't reflect it. And so you transfer those to the drum, and then you pick up the ink there, and then that gets transferred to your paper. Okay, so electrostatics, it's a little bit more complicated than just straight electrostatics, but it all works because of electrostatics. And then I always like to show this video. Here's my... This is a surveillance camera at a gas station. So starts pumping gas, gets back in her car, slides back out across the seat. Oh, a little spark gets generated. She's pretty calm. Yeah, if that ever happens to you, run like hell. Don't stand there trying to put it out. So anyway, what does she do? she gets back into her car, right? And then slides out across the seat of her car and doesn't touch anything, doesn't touch any metal, doesn't discharge herself until right there. And she gets a spark, and that causes the gas fumes to ignite. So in California, we have those sleeves that catch the fumes, so that would probably prevent that from happening. And then it's always a good idea just to discharge yourself when you get out of a car. She's not grounded with the floor because this is just, let's see, it's probably just a concrete floor. She may have had, rubber tennis shoes or something that are insulating. Her shoes probably aren't conductive. So when you get out of your car, just grab the door, touch the door, touch the side of the car, touch some metal, and you'll discharge yourself. I usually do that because it seems like I get a shock every time I get out of my car. And if I don't know it's coming, right, it surprises me. It seems to hurt more or whatever, than if I know it's coming. So as I'm getting out of my car, I just grab the door and get it over with. Of course, this is more prevalent in dry weather when there's a lot of humidity in the air. It's hard to build up static charge. And so this happens more in dry weather. Okay, so the reason I like that video so much is because the next time you're at the gas station, you're going to be thinking about physics. That's right. Okay, moving on here. Let's do this one. So we'll start with the first case here. Two charged particles are fixed in place, lowercase q and capital Q. Capital Q is greater in magnitude than lowercase q. A third charge is now placed at one of the points, A, B, C, D, or E. The net force due to the other two charges is 0. Can you charge your car with static? I think so, because your car is pretty well isolated, right? It's on rubber tires. It's pretty well isolated from ground. So I think your car can pick up electric charge. Okay, so number one here says, at which point is it possible to place a third charge such that its net charge is 0? Yeah, remember our force kq1 q2 over r squared. So in order for the forces to be the same magnitude, right, we want them to cancel each other out. In order for those forces to be the same magnitude, we have to be closer to the smaller charge. You see that? Closer to the smaller charge. And where do we have to be for them to cancel out? Outside of the two charges or between them? Between them, that's correct. So if we put a charge, and what doesn't matter whether the charge we're sticking there is positive or negative? let's put a negative charge there. Let's put a negative charge somewhere in between here. We're going to stick a negative. I'll use a different color, a blue. We're going to put a negative charge somewhere in between here. So a negative charge interacting with this charge is going to feel a force to the left. They attract each other. Negative and a positive attract each other. A negative charge interacting with the capital Q is going to feel a force to the right. So those were okay, right? Those might actually cancel out. If we pick the right location, we might get those to cancel. They point in opposite directions. We might get those to cancel. But if we stuck that charge out here, let's rethink this. Let's put that charge over here. The negative charge with the small, what did I use? Green? Those are going to attract. And the negative charge with this positive charge is also going to attract. Those can never cancel to zero. They both point in the same direction. They'll never cancel each other out. So you have to be between them for a negative charge, right? Now let's put a positive charge there. The positive charge with this small q is going to repel. We're going to get a force to the right. The positive charge with the capital Q is going to repel the capital Q. It's going to get a force to the left. So positive, negative doesn't matter. You have to be in between the two charges to have any chance for them to cancel to zero. So we know we have to be in between. We can't be out here. We can't be out here. We have to be in between. Now the question is, where in between? Well, we said we have to be closer to the smaller charge in order for the magnitudes to be the same. First thing we thought about was the directions. That told us we had to be in between the two charges. The second thing we're thinking about is the magnitude. We have to be closer to the smaller charge. So the answer would be B. All right. Let's take a look at the next example, see if you're getting it. So the lowercase q is the same, but the capital Q is now negative. So these are now this one has changed. This one's now negative. You see that? Capital Q is greater than magnitude of charge than lowercase q, yes. So now what you want to think about, do we have to be in between the two charges or outside of the two charges? So if you put a test charge here, let's just make it positive. We know it doesn't matter what's the sign of the test charge is, right? If you put a test charge in the middle here, then from the lowercase q, we get a repulsive force. And from the capital Q, we get an attractive force. They point in the same direction. So we can't have it in the center there. But if we put it outside, either location, it doesn't matter. If we put it outside, then from the small q, we get a repulsive force. And from the capital Q, we get an attractive force. Now there's a chance that those two might cancel to zero. We have to be outside of the two charges. Okay. Now we say to ourselves, what about the magnitude? We need the magnitude of this one to be the same as the magnitude from the other charge, right? So that means we have to be closer to the smaller charge. So we have to be at location A. We can't be at E. Okay. Did my sound go crazy? Sorry about that. Am I back? Okay. Okay, sorry. I guess there's nothing I can do about that. Okay, next one. Now the lowercase q is negative and the capital Q is positive. So because these charges are oppositely signed, or opposite signs, I guess I should say, they have opposite signs, little q and capital Q, we know we have to be outside. Think it through for yourself if you need to. We know we have to be outside. We can't be between them. And we know we have to be closer to the smaller one. So A. And the last one, we're going to change both of these to negative. The small charge is negative. The large charge is negative. So we have to be in between now, in between, and we have to be closer to the smaller one. So B. Yeah, so you're walking through, think about, just stick a charge. Let's go back. Which one do you want to do? The third one? Stick a charge over here. Where do you want it? In between. Let's stick a charge in between. Doesn't matter, positive, negative, stick a charge in between. And say, what's going to happen now? If I put a positive charge in between these two, from the one on the left, I'm going to get an attractive force, right? The positive and the negative to attract each other. From the one on the right, I'm going to get a repulsive force. So both of those forces are going to be in the same direction, though they can never cancel out to zero if they both point in the same direction. So we can't be in between. Yeah, we're looking for a point where the, let's go back. We're looking for a point where the net force is zero on this charge that we're putting in there. Okay, excellent. Okay, let's do this one. So we've got two charges, A and B here, fixed in place, and a third charge, C, over here, also fixed in place to the right of the other two. The distance, twice the distance between A. So this, if this is D, then this is 2D. Is that right? There's no net force on C due to the other two charges. And they're given, this is positive, and this one's negative. The signs of the charges are given. And the net force on C is zero. So what can you determine from this? Charge A has a greater magnitude than C. Charge A has a greater magnitude than B. There's a bunch of questions here. See which boxes you can check. let's think about the forces involved here. A and C are both the same sign. So the force on C due to A, I'll call that FA, has to point to the right. The force on C due to B is going to point to the left. Call that FB. And we know that FA and FB have to have the same magnitude because they net to zero. Okay, so if you think about it this way, right, we know the forces, they gave us the signs of the charges, so we know the forces point in opposite direction. They tell us they net to zero, so that tells us the magnitudes have to be the same. And once we plug in write out what the magnitudes are, we see that QC cancels out. It doesn't matter what charge we put at C, it's gonna cancel out of the equation because it's the same in both equations, right? Whether if we know FA and FB are equal, it doesn't matter if we multiply both by a big number or both by a small number, they're still going to be equal, right? And that's what C is doing, really. So this first one here cannot be determined. C is irrelevant, right? It drops out of the equations. Now we know that the distance between A and C is bigger than the distance between B and C, so that means that the charge A has to have a greater magnitude than charge B. We good with that one? Now we're comparing A and C again. We don't know. We don't know anything about C, right? Question is, how can you get these to cancel if the charges are different or the distances are different? Because the charges have different magnitudes, right? So yeah, QA and QB are different. Now it says charge A is the same magnitude as B. That's not right, right? We know already. We already said that one of them had to be bigger. A had to be bigger, right? And now we're comparing C with something. We don't know what C is, right? So that doesn't. Okay. All right. You can do this one on your own later. Similar, same type of problem, but now the net force on B is zero. You can do it later on your own. All right, so let's think about what we've got going here. We've got electric fields from charges, right? So we've got some charge Q And we want to know what's the electric field over here. We use this equation. We need to know the distance, right, between these two points. And we use that equation. Now we say, what about if we have multiple? Multiple point charges. So we've got a Q1, we've got a Q2, we've got a Q3. Let's make these positive, positive, negative. And we want to know what's the electric field over here, right? So what do? We've got a, we say Q1 is producing an electric field over here. What color should I use for Q1? E1, right? And then we say Q2 is producing an electric field over here. It points away from Q2, right? And then we have Q3 points toward Q3, right? So it's going to be something like that. And then we do the vector addition. We add them up. We've got E1 we've got E2 and we've got E3 and we add them up, and what do we get? We get this vector right here, right? So our net electric field is the vector sum, right? Be okay with that? So we add them up. What's that called? Superposition, right? We just add up the field from each individual charge, and that ends up being the net field. So, okay, we get a single point charge. We've got multiple point charges. What's next? So now we want to know, how do we find the electric field from a continuous charge distribution? Let's say we have a rod that's charged up, or a sphere, or a disk. So let's take this example. We've got a we've got a rod here, and so it has some length, right? This is going to be L over 2 and minus L over 2. And let's give it, I don't know, let's give it positive charge. Uniformly distributed along the length of that rod. length L, total charge Q. So we want to know what's the electric field at some point on the y-axis there. Okay, so what are we going to do? Well, what did we do? When we had a point charge, we knew our equation, right? Our equation is just kq over r squared. When we have multiple point charges, we add up the field from each individual point charge. So when we have a continuous charge distribution, what do? We pick some, yeah, I'm seeing people integrate. Yes, we pick some little tiny part of it, right? Some little tiny chunk. And we say that little tiny chunk is like, it's so small, it's like a point charge, okay? And we treat it like a point charge, and then we add up the effects from every little chunk that makes up the whole thing. So there's a little tiny amount of charge here. We call that dq. A little tiny amount of charge out of the whole charge distribution. And so the electric field over here, I guess I need to create a so that dq, that little tiny amount of charge, creates some little tiny amount of electric field at our point of interest. I'm going to call that dE. And then I'm going to add up all the dEs from all the dQs and get my total electric field at that location. So what is dE equal to? Well, the electric field is K from a point charge. We're treating this little tiny element of charge as dQ. We're treating it like a point charge. So what's the electric field from a point charge? It's K times the charge over r squared. So this would be K. My charge is dQ, right? So that's my starting point. Now, what do I want to do? I want to add them all up. I want to integrate. What's the problem with that? The problem is this is a vector quantity, right? So if I pick a different, let me go with blue. If I pick a different dq, then that's going to create an electric field that points in this direction. And electric field is a vector quantity, right? I have to break these up into components before I add them up. So I can't integrate until I break it up into components. There's another problem, right? dq. What the heck is that? How do you integrate q? Well, let's get rid of dq first. Let's figure out how we turn dq into something we can integrate over, right? In this case, maybe dx, right? That's what we want to turn it into. So let's get dq into something we can integrate over first. Once we've done that, we'll split this up into components. Then we can integrate. Okay, so how do we deal with dq? How much charge is in that little tiny chunk there that I picked? So let me ask you this question. If I gave you a long rope, and I said, I want to know how much 1 meter of the center of that rope weighs, but you can't cut my rope. What are you going to do? You're going to weigh the whole rope, right? And you're going to measure the length of the whole rope. and you're going to figure out what the density of the rope is. Then any distance, any amount of length in the middle, you just multiply by the density and you get the mass of that section, right? That's the same thing we're going to do here. We're going to say that this little chunk in the middle has some length. We know it's going to have some small length associated with it. Well, what's the length associated with it? It's going to be dx, right? The little tiny element of length here is going to be dx. That little amount of charge is located in a little tiny length along the axis there. So it's the distance multiplied by the density, right? Okay, we're trying to find how much charge is in a little tiny length along our rod. Well, we take the length and we multiply it by the charge density, the charge per unit length, right? Charge density is charge per unit length. And that gives us the charge. So we've got the charge density multiplied by the length, which is dx. And in this case, if it's uniform density, doesn't have to be uniform density. If it's uniform density, this is Q over L, total charge over the total length, times dx. If it's not uniform density, you're told, you're probably given some function for the charge density, and you just stick the function in there. All right. So there's our, so now we've sort of converted this into something we can integrate over, right? We've got dE is equal to K Q over L dx over R squared. Okay, we're halfway there. So we know we're going to integrate over X. How do we know? Well, a couple of things. We have to add up all the DQs. We have to integrate over the charge distribution, right? If every little element of charge, right? There's one over here, there's one over here, there's one over here. Every little element of charge that makes up this whole rod, we have to add up its contribution to the electric field. So we have to integrate over the whole charge distribution, and it's located along the x-axis. And when we got our dq, the dq told us we're integrating with respect to x. So we want to turn everything into a function of x. Anything else we want to get in terms of x, because we know we've got this integral in terms of dx. So what is r? So k, q, and l are constants. We're good. We don't have to worry about those. But we've got this r in our equation. What is r? R is the distance from our charge, dq, to our point of interest. So r is this distance right here. Let me, what color am I going to use? R is that distance right there. And this distance has to be given. So let's make up some number here. Let's call that A. Some distance A away from the rod. Okay. So now we can turn. We know our dq is located at a distance x, a position x. A is a constant. So now we can write r in terms of x. So we can plug that in there, and we get our dE is k lambda dx over x squared plus a squared when we square it, that's what we get, right? Okay, so we've gotten rid of our dq. We've got it in terms of something we can integrate over, right? We've got it in terms of dx, and we've converted our r in terms of x. So we're pretty well set now. But before we integrate, we have to use components, right? I'll write that in big red letters. Okay, so we need to find the x component and the y component of our small amount of electric field caused by dq. Okay, I'm going to get rid of this one. All right, let's get rid of that one. Okay, so we want to split this up. So let's pick an angle. How about, I would probably pick this angle right here. Call that theta. And then the y component, if I pick that as theta, the y component is going to be dE times the cosine of theta. You see that? And the x component is going to be dE sine theta, right? Because the x component, I'll use blue. The x component is this one, right? So that's the opposite of theta, right? And the y component is this one, and that's the adjacent side. So if we pick that as our theta, you could pick other angles as theta too. You could pick, you know, so you have cosine on the x and sine on the right, but your theta would be different, right? I'm gonna just, this is easy. I look at my picture and I see that theta is nice and easy one to find. So I use that. Okay, so that created a little, so let me go back, let me plug in here. So I've got K, Q over L, dx over x squared plus a squared. And now I have a sine theta here. So just when I thought I had this whole equation in terms of x's, now I've got a theta in there, and that theta is a variable, right? It changes as my dq moves out and along that. As I integrate, I'm going to integrate, the dq is going to change location, theta is going to change. It's a variable, it's not a constant. So I need to get it in terms of x's, right? I can't have a sine theta in there. I'm integrating over x. I need to convert it into an x. Well, what is the sine of that angle? I've got a triangle here. Here's my triangle, right? I got a triangle here. And I can look at that triangle and I know that the sine of theta has to be the opposite side over the hypotenuse, x over r. You see that? X over r. I'm going to get rid of that guy. So the sine of theta is x over r. And what is the cosine of that angle? It has to be a over r. You see that? Question about using components. You have to use components because we're adding up all the dE's, right? And one of the dE's points in this direction. So if this is our point of interest, we have way out here at the end of the rod, we have a dE pointing in this direction. And over here, we have a dE pointing this way. And over here, we have a dE pointing straight up. And over here, we have a dE. We want to add all of those up. If it was a scalar, yeah, we just add them up, no problem. But it's a vector quantity. Electric field is a vector quantity, and you can't just add two vectors that don't point in the same direction. So we need to break these up, each one of these, into an x and a y and x and a y and x and a y. We need to break each one of these up into an x and a y, and then we add up all the y's and we add up all the x's. Once we split them into components, then we can add them all up. And what is an integral? You're adding up a bunch of stuff, right? Okay. Okay, so let's get rid of the sine theta. We want everything in terms of x. This tells us everything has to be in terms of x. That's what we're integrating over, right? Once you know that you have a dx in there. All right, so what do we have? We have k q over L dx. And now we also have an x. Well, I'll just put that separately here. An x over r. And what did we can't have an r in our equation, right? That's also a variable, but we know what r is. R is x squared plus a squared square root. So this is our sine theta. And we can simplify that a little bit because the denominator is the same. We've got k, q over L. Those are all constants. X dx over x squared plus a squared to the 3/2 power. And so we integrate both sides and we say e sub x is equal to the integral of this. And I guess yeah, that's fine. And what are we integrating over? What are our limits? We're integrating over the whole charge distribution. So x is going from minus L over 2 to plus L over 2. So our limits of integration here, minus L over 2 plus L over 2. Now, you probably have learned how to do integrals like this. That's math. That's great. You should know how to do that. In my class, I would just look this up on an integral table. So if you flip to the back of your physics textbook, they probably have integral tables in there. If you look on the second sheet of the formula sheet, there are integrals. There's a little small integral table there. So I would just look this up in my integral table and get the answer that way. And that's how I would solve that. And that's how I would expect you to solve it on an exam. You can use the formula sheet on every exam. So you should assume that you're gonna print it out and start using it when you're doing problems so you become familiar with it. And then you do the same thing for the y component. I'll let you do that on your own. Do the same thing for the y component. And what do we know about, let's take a quick look here. What do we know about the electric field on the y-axis there? So if you question about leaving it like this on the exam, you would not get full credit, but you'd get most of the way there. You'd have most of the points. But I do want to see you evaluate that integral, even though you're looking it up on an integral table. Okay, so what do we know about the electric field on the y-axis? We know it only has a y component. E sub x has to be 0, right? By symmetry. Every point on the left side has a component this way. Every point on the right side has a component this way. In the x direction, they cancel out. In the y direction, they add together. So we know E sub x has to be 0. So if I was doing this on an exam, the very first thing I would write is e sub x equals 0 by symmetry. And then I would only solve it in the y direction. But since you're just starting out, this is a perfect case. Students always want to have the answer to a problem, right? Oh, I don't like doing the even problems because I don't have the answers to them. Well, here you have the answer to it. You know e sub x has to be 0. Do it and prove to yourself, go through and do the calculation and see if you get 0 when all is said and done here. If you don't, you did something wrong. Okay? So what I'm going to do is stop the video. I'll stick around here for a little bit and answer some questions. And then we'll pick it up again on Friday. And some of you I will see in lab, but we'll start lab. Just a reminder, we're going to start lab at 12:15, okay? 12:15, so it gives you a little bit of a break to grab a bite to eat, stretch your legs, whatever you're going to do. Okay, I'll stop the video and then I'll stick around and answer some questions.